Well, now here's a question. Could nuclear fusion supply endless clean energy?
No fewer than 35 nations are teaming up and combining their strengths to build something that's never been built before.
Successful nuclear fusion has long been a dream for scientists worldwide.
Right. There are projects that feel big because they're expensive. And then there are projects that feel big because they're trying to do something. Nature normally reserves for the inside of stars. ITER is one of those. International Thermonuclear Experimental Reactor. 23,000 tons of machinery. 150 million degrees at the center. 4 degrees above absolute zero, just meters away. A temperature gradient that shouldn't exist in one device. And a price tag past $65 billion. This is the most complex scientific collaboration in human history, and it might be the only realistic path to unlimited clean energy. What ITER actually is. People call ITER the fusion reactor that will power the future. Good headline. Slightly misleading. Because ITER won't power anything. No turbines, no generator hall, no grid connection. It's not designed to sell electricity. ITER is a laboratory machine built to answer one question. Can we make fusion produce far more energy than we put in, and keep it stable long enough that the next step becomes engineering, rather than wishful thinking? The key idea, a fusion power plant only makes sense if the plasma can largely heat itself. The fusion reactions must contribute enough energy that you're not constantly forcing the plasma to stay hot. That's where Q comes in. Q is the ratio between fusion power produced and heating power injected. If Q equals 1, you've reached break even. If Q is much larger, the physics starts looking like something you could build into a reliable system. ITER's target. Q equals 10. 500 megawatts of fusion power from 50 megawatts of input. Sustained for hundreds of seconds. Even if ITER hits that target perfectly, it still won't be a power plant, but it will prove the core physics and control problem can be solved at the scale a power plant would need. ITER is the bridge, not the destination. Fusion and the Tokamak. Fusion sounds straightforward until you try to do it in a machine. Take two forms of hydrogen, heat them until they become plasma. A gas so hot that electrons detach from atoms, persuade them to fuse. A small amount of mass becomes energy. On the Sun, gravity provides the pressure. On Earth, we create the conditions ourselves. The challenge, the fuel has to be hot enough to fuse, and it has to be kept away from everything. Because the moment plasma touches a wall, it cools instantly. The fusion stops, and you're left with a machine extremely good at turning electricity into disappointment. To make fusion worthwhile, you need three things. Hot enough, dense enough, confined long enough. If one drops, the whole thing collapses. To keep something that hot away from everything, you need a container that isn't really a container. ITER uses a tokamak, a large, hollow ring where plasma is held in place by magnetic fields instead of walls. That sounds elegant. The reality is controlled stubbornness. A plasma is not a polite guest. It moves, it wriggles, it finds weaknesses. The tokamak's job is to shape magnetic fields that keep the plasma away from the vessel, and stable enough that it doesn't develop the kind of instabilities that end your experiment in a fraction of a second. There's a clever feedback loop. The plasma conducts electricity, so ITER drives a current through it, millions of amps, and that current becomes part of the magnetic structure that confines it. Mental picture. Imagine a smoke ring. Now imagine the smoke is hotter than the sun's core, and instead of air, the ring is suspended inside a magnetic cage that has to be strong, smooth, and constantly controlled. Here's why ITER is such a beast. Size helps. A bigger plasma holds its heat better relative to how it loses it. The tokamak is a compromise between physics and engineering. A magnetic bottle built large enough that confinement isn't a heroic moment, but a sustained, controlled condition. Extreme engineering. Now ITER stops sounding like a normal engineering project and starts sounding like several different projects, forced to share the same machine. At the center, plasma aiming for 150 million degrees Celsius, just meters away. Superconducting magnets that only work at temperatures close to 4 Kelvin, a few degrees above absolute zero, inside one device. Two extremes that have no business being neighbours, hotter than the sun's core. Hardware living in conditions closer to deep space. The engineering trick isn't cool the hot bit or warm the cold bit. It's maintaining a sharp boundary between them, heat where you want it, cold where you need it, stability everywhere else. That means vacuum systems, cryogenics, thermal shields, and an amount of insulation that would make a space engineer nod quietly. The magnets, 18 enormous toroidal field coils, each 17 meters tall and 300 tons, wrapped around the vessel like orange segments, cooled to minus 269 degrees Celsius. At the heart sits the central solenoid, a stack of superconducting modules with a total mass around 1,000 tons. It generates 13 Tesla. An MRI machine uses 1.5 Tesla. The central solenoid is nearly 10 times stronger. This thing was manufactured in San Diego, shipped across 2 oceans, transported 104 kilometers through French countryside on a convoy moving at walking speed. At night, for 4 nights. Too big to fit under bridges during the day. Fusion is very obviously an engineering problem. Not just can we do it, but can we do it reliably, safely, repeatedly, with hardware that survives? In ITER, the plasma is not the only thing under stress. Everything is, built by the world. Why is ITER so difficult? Forget the plasma for a moment. Think about shipping. Normal project. Main contractor, supply chain, purchasing department. We need this part. Built to this drawing. Delivered on this date. ITER isn't built like that. The machine is delivered as in-kind contributions. Partners don't just pay money. They deliver major hardware, coils, vessel sectors, power systems, whole subsystems, built around the world, brought to one site, expected to behave like one coherent machine. The EU builds 5 of 9 vacuum vessel sectors. Korea builds the other 4. Japan makes toroidal field coils. The United States manufactures the central solenoid. India builds the cryostat, a 3,850-ton steel thermos flask. China supplies magnet feeders. Russia provides specialized port plugs. A jigsaw puzzle designed by 7 countries, using 7 industrial standards. Every piece must fit with sub-millimeter precision. Then you have to move them. Components so large and heavy that ITER created its own logistics choreography. A dedicated route of 104 kilometers from port to site. Convoys carrying loads approaching 900 tons, including the transporter. Components arrive at Fos-sur-Mer, loaded onto a barge, cross the Étang de Berre, loaded onto a specialized transporter. The roads weren't built for this. France spent 170 million euros rebuilding every bridge, reinforcing every overpass, widening every roundabout. The ITER Itinerary. Convoys inch forward, streetlights removed, traffic signs dismantled, police escort at walking speed. 4 to 5 nights to cover 104 kilometers. One component, the cryostat base, measured 22 meters long, 11 meters wide. Took 5 nights. The French Postal Service moves faster. On site, assembly hall tall enough to swallow giant components. Cranes lifting 1,500 tons in combined capacity. Thousands of people working. Roughly 1 million components. The machine is enormous, but the real complexity isn't size, it's integration. If one piece is late, it can block access, freeze an installation sequence, delay 10 other tasks, because the physical order of assembly is not negotiable. When a project is built by the world, the biggest risk isn't that a component is badly made, it's that a perfectly good component is made to the wrong version of correct. ITER runs on simple discipline, one approved definition of the machine, one version of the truth, shared across everyone who designs, builds, inspects, installs. Sounds boring. It isn't, because when that discipline slips, consequences don't arrive as a warning, they arrive as a delay. What broke? When ITER announced a major schedule shift in 2024, it wasn't project politics. It was the real-world consequence of building first-of-a-kind hardware at extreme scale. First plasma moved from 2025 to 2034. 9-year shift. 5 billion euros in additional cost. Tempting to imagine a problem made of meetings, but the truth is simpler. Very physical engineering failures, the kind you can't negotiate away. You cut, rebuild, requalify. Thermal shields. Between the vacuum vessel and superconducting magnets sit panels designed to block heat transfer. Actively cooled. About 23 kilometers of cooling pipes. 2022. Inspectors found hairline cracks in welds. Not a few, thousands. Stress corrosion cracking tied to the silver plating process. Chemistry doesn't care about your schedule. The fix? Slow, methodical work. Removing pipe sections, reworking panels, rebuilding. Full qualification cycle. Years absorbed. You don't patch critical hardware that must be vacuum tight and cryogenically stable. Vacuum vessel sector number 8. Arrived with dimensional nonconformities in welding bevels. That phrase sounds harmless. It isn't. When you join two massive pieces, the prepared edges, the geometry that makes proper welding possible, don't line up. At this scale, you don't persuade, you correct. Building up material, machining back to recover intended geometry, requalifying the weld preparation. Another year gone. The only acceptable outcome. Correct, proven, documented. Simple lesson. ITER is not delayed because fusion is fantasy. It's delayed because building the most complex machine forces reality to show up in precise places. Welds, coatings, tolerances, inspections. Reality is binary. Either the component meets the definition or it doesn't. What happened next? The project didn't stop, didn't pretend problems were minor, reset the plan, resequenced work, kept assembling. The geopolitical miracle. One aspect almost never makes it into technical brochures, yet might be the most surprising feature. ITER is a machine built to study fusion. It's also a long-running experiment in cooperation. The origin, Geneva, 1985. Ronald Reagan and Mikhail Gorbachev. Height of the Cold War. They pushed the idea that fusion should be developed collaboratively for peaceful purposes. That explains why ITER is organized as an international program, not a national one. 2006, project launched with 7 members. The EU, United States, Russia, Japan, China, South Korea, India. A large share of the world's population. At times, a fairly impressive share of its disagreements. The collaboration has continued. Through Brexit, through COVID, through political shifts, sanctions, crises that would normally freeze cross-border programs. Hardware keeps arriving, interfaces keep getting negotiated. Installation keeps moving forward. Russia is still a member, despite sanctions. November 2025, Russia delivered a critical component, the PF-1 coil, 200 tons, manufactured in St. Petersburg, shipped through NATO countries, arrived without incident. One of ITER's most important proofs, not a plasma measurement, but a demonstration that complex engineering can be a bridge between geopolitical islands. Physics doesn't take sides. A flange doesn't care where the bolt was manufactured. In a world increasingly comfortable with fragmentation, that's an unexpectedly valuable thing to build. Success and the path forward. What does success actually look like? Not a single heroic moment where someone presses a button and the future arrives. ITER's success is quieter. A series of measured proofs that the machine can do what it was built for, repeatably, under control, with numbers that finally behave. Q equals 10. 500 megawatts of fusion power from 50 megawatts of heating, in pulses of hundreds of seconds, long enough that stability, control, heat handling become real-world problems rather than quick demonstrations. In fusion, achieving the conditions for a moment isn't enough. You have to keep them. That's where engineering lives. Plasma control, heat exhaust, material behavior, Diagnostics that tell you what's happening. Systems that do this repeatedly without turning the machine into a one-shot experiment. First plasma, the machine's first controlled heartbeat. Basic magnetic confinement, vacuum, power, controls working together to form and hold plasma. Not full performance. First proof the integrated machine behaves like a tokamak rather than a very expensive sculpture. After that, step by step, through more demanding phases, building toward burning plasma, where fusion reactions meaningfully sustain the plasma's own temperature. If ITER gets there, it still won't be a power plant. What ITER does removes the biggest uncertainty. Can we run high-performance fusion plasma at scale with stability and control a real plant would need? If yes, the next step becomes concrete. Demonstration power plant focusing on electricity production, higher availability, maintainability, practical realities of operating fusion as infrastructure, not experiment. ITER's success isn't fusion power for everyone, it's more specific, more valuable at this stage. A credible, measured, repeatable proof that the hardest physics and control problem can be solved at the scale a future power plant requires. The bottom line, ITER is often described as a gamble. It is decades of work, huge infrastructure, uncomfortable amount of money invested in a machine not guaranteed to deliver clean success on a neat timeline. But it's also something else. A demonstration of what modern engineering looks like when the problem is bigger than any single organization or country. Inside, a lesson in extremes. Controlling plasma at 150 million degrees while magnets sit degrees above absolute zero. Handling forces and heat loads pushing materials to limits. Outside, a lesson in integration, taking hardware built around the world and assembling it into one machine with one definition of correct. The human lesson. The hardest part isn't always the science, it's the discipline. Interfaces, documentation, verification, sequencing, the patience to fix things properly when they go wrong. If ITER succeeds, it won't instantly solve energy. What it will do, move fusion from promising to engineering plausible. Make the next step a rational decision rather than hopeful leap. Even if fusion takes longer than we'd like, ITER will have achieved something quietly important. Shown we can organize complexity without pretending it isn't there. Build one machine from many countries. Sometimes the most impressive part of the future is not a breakthrough moment, but the steady, methodical work required to make a breakthrough possible. 2034, if everything goes to plan, the machine turns on. Plasma heats to 150 million degrees. Magnets hold. Proof that fusion at scale is not science fiction. ITER is defining what the next century of energy looks like. One way or another. Subscribe for more engineering deep dives into humanity's biggest machines. Comment, will fusion work?